Hi everybody. So this next section 2.4 has to do with one-sided limits, and we've kind of talked about this a little bit when we talked about limits, but the idea in this case is we're talking about what happens if you approach a limit from the left or the right-hand side. And as we've seen before, in some of those examples, where we had a discontinuity, if you're approaching a value from the right as x approaches the point from the right, or as it approaches from the left, you can get two different values from the limit. And so the number to which a sequence of values of a function evaluated at the x values on one side or the other of the x value of interest converge, right? That's the definition. And we'll have some special notation for this. The little plus here just means you're approaching c from the right-hand side, and the little minus here just means x is approaching c from the left-hand side. Otherwise, it's very similar to the notation we had before. So again, let's say we've got this function, and the limit of f of x as x approaches 2 from the left is equal to 4 would be written this way, right? Because you're approaching from the left, you'd put the little minus sign there. And the limit of f of x as x approaches 2 from the right would be written this way. And so we'll see that all of the regular rules for limits that we saw for regular limits also apply to right and left-hand limits. So I don't know if you really need to write these down or anything. Right, and here's sort of a visual idea of what's going on, right? So x is getting closer and closer to c here, and so the height of the function would get closer to L from the left, or in this case from the right, and in this case from the left, right? And you can see the little plus or minus there. So here's one example. We looked at some examples similar to this, but again, you can have functions that have different right and left-hand limits. So the limit from the right in this case would be 1, but the limit as x approaches 0 from the left would be negative 1. So in this particular case, right, I guess we have the same value here, right? As x approaches 2 from the left, you get 0, and as x approaches negative 2 from the right, you get that the height is 0 also. I guess you can't really talk about the limit from the left here or the limit from the right because there's no function defined there. So a function f of x has a limit as x approaches some number c if and only if it has a left and right-hand limit and those limits are equal. So for example, going back to this example, in order for a limit to exist, the left-hand limit has to exist, the left-hand limit has to exist, the right-hand limit has to exist, and both of the limits have to be equal. So in this particular case, this function does not have a limit, because although it has a right-hand limit and a left-hand limit, they're not equal, right? The right-hand limit is 1 and the left-hand limit is negative 1. So another way of saying that in terms of, I guess, a more formal way is the limit as x approaches c of f of x is equal to L if and only if the left-hand limit of f of x as x approaches c from the left is equal to L, and the limit as x approaches c from the right of f of x is also equal to L. So just for some practice here, for the following graph, let's say we want to determine the left limit, right-hand limit, and the overall limit at x is equal to 0, 1, 2, 3, and 4 if they exist. So if you look at when x is 0, right, well, there's no left-hand limit because the function doesn't even exist there. Right, I guess the right-hand limit would be 1, but since the left-hand limit doesn't exist, right, then there is no limit for that function. When x is equal to 1, the left-hand limit is 0. The right-hand limit approaches height 1, but they're not the same, so the limit doesn't exist there. Right? For 2, the left-hand limit is 1, the right-hand limit is 1, so the function would exist there and would be 1, again, even though the function is defined differently there. Right? The limit as x approaches 2 from the left to the right is height 1. When x is equal to 3, the left-hand limit would be 2, right-hand limit would approach height 2, the overall limit there would be 2. For this function, the limit from the left-hand side would be 1. There is no right-hand limit, right, so the function would not exist there. So this is just a restatement of all the answers I just gave you. You can pause the video and look at this if you want, but this is basically what I just said. Here's another example. Let's say we want to determine The following results are true or false based on this graph, right? So here I'm just kind of getting used to the notation. So I'm saying here the limit as x approaches -1 from the right, is that equal to 1, right? So does the function approach height 1 from the right as I'm approaching -1? Yeah, it looks like it. So that one would be true. The limit as x approaches 2 of f of x does not exist. Well, so as x is approaching 2, from the left and the right we both get 1, so that would be false. The limit does exist and it's 1. For C, what's the limit as x approaches 2 of f of x? Well, in that case we're saying that it's equal to 2, but that's not right. We just saw that the limit is 1, so that would be false. It approaches 1, although the function itself, evaluated at 2 is at 2 is 2, right? The limit, the height that the limit approaches is 1 there, so that would be false. For D, the limit as x approaches -1, or excuse me, the limit as x approaches 1 from the left is 2. So I'm approaching 1 from the left. Yeah, it looks like the height there would be 2, so that would be true. E, the limit as x approaches 1 from the right is equal to 1. Is that true? So I'm approaching 1 from the right. Yeah, it looks like that approaches height 1, so that would be true. The limit as x approaches 1 does not exist. Well, in order for the limit to exist, the limit from both the left and right hand sides have to be the same, so that would be a true statement, right? The limit does not exist there. The limit as x approaches 0 from the right equals the limit as x approaches 0 from the left. Yep, they both approach the same height, 0. The limit of f of x as x approaches c exists everywhere at c, exists at every c in the open interval from -1 to 1. Right? So in the open interval that's true because for every point the limit from the left and right hand side approach the same height there. Right now at 1 itself there's no limit, but this is not including 1 and -1, so that would be true. I guess I forgot to mark that one true. The limit as x approaches c of f of x exists for every c in the open interval from 1 to 3. Yeah, that's true, right? The limit does exist there. The function might be defined differently there, but the limit does exist, so that would be true. The limit as x approaches -1 from the left, what's that? Well, as you're approaching -1 from the left, you can't do that, right? I mean, you can't approach -1 from the left because the function isn't even defined there. And the limit as x approaches 3 from the right does not exist. And that's true because the function isn't defined there either. Right? So here's the answers to all these again. Hopefully that'll match what I just had on there. But again, you can pause the video and look at this if you want. So this brings us to the formal definition, or the technical epsilon delta definition of the right and left hand limit. I don't think you really have to worry about these. I'll just kind of read through the definition. It's similar to the definition we saw in the last section, but we say that a function has a right hand limit at x sub 0, and the limit is as x approaches x sub 0 from the right of f of x is equal to L if for every number epsilon there exists a corresponding number delta, such that for all x between x sub 0 and x sub 0 plus delta, you'll notice we're not subtracting a delta on the left hand side because it's a right-handed limit here. Then the height of the function is within epsilon units of the limit L, right? And similarly, we say that f has a left-handed limit written this way if for every number epsilon there exists a corresponding delta, such that for all x, again, you can't really define the limit to the right of x sub 0 because it's a left-hand limit, right? So x sub 0 minus delta, right? So there's no plus delta like in the definition we saw in the last section. Then the height of the function has to be within epsilon units of the limit L. So don't worry too much about that technical definition. I'm just going to skip these slides here. Now one thing I want to mention is, again, there are other weird things that can happen. Here's the function 1 over x. We've seen this before. And again, although this function seems like it would be continuous, there is no limit from the left or right hand side because the function keeps oscillating too rapidly and it doesn't ever settle down to anything. So this function does not have a right or left hand limit. I typically won't ask you weird questions like that in the exam, but just something to be aware of. Typically I'll ask you questions more like this one, like what is the left or right hand limit of various functions? And so this is similar to problems I think 11 through 17 in the book. If you have a copy. But the idea in this case is, again, just like before when we were evaluating limits in 2.2, just plug the number in first and see what you get, right? So if you're approaching 1 from the right, you get 1 minus 1 over 3. Well, that's 0 over 3. The square root of 0 over 3, that's just 0. Right? Again, you can have sort of more strange things that can happen. Again, as you're approaching 1 from the right, if you think about what this function is, this is just the function, that absolute value. If you think of x over the absolute value of x over x that we saw before, that looked like this. That would just be this function shifted 1 to the right. So as you're approaching 1 from the right in this case, you may have to do some of these graphically. They may not always be algebraic. But as you approach 1 from the right, this takes on a value of 1. This would also take on a value of 1, so that'll just be the square root of 2. But if you're approaching the function from the left-hand side, right, that takes on a value of -1. This takes on a value of -1. So you'll get a 2 times 1, square root of that's 2, but then you'll have the negative. So some of these you might have to kind of play around with a little bit. Here's another example. Let's say you want to take the limit of this as h approaches 0. Well, again, this is one with a square root in it, so remember, like I said before, if you have a square root in it, try multiplying by the conjugate like we did back in 2.2. So these problems will be pretty similar to what we did in 2.2, except they'll just be left or right-hand limits. So in this case, just go ahead and multiply on the top and the bottom by the conjugate, right? Just change the negative to a plus, and then just go ahead and FOIL that out, right? The top looks like it's going to be messy, but remember, so the form of a minus b times a plus b, so that'll just be the square root of 6 squared, which is 6, minus the square root of 5h squared plus 11h plus 6 squared, which will just wipe out the square root. On the bottom, just leave that for now. Just take the h times that, and then simplify the top here, right? Now I think you'll see some things will cancel here, like the 6 will cancel with a -6 there if you distribute. So you'll be left with a negative 5h squared plus 11h. If you factor that negative h out, you'll see that that h will cancel with one of the h's on the bottom. And then try taking the limit again in this case. It really doesn't matter in this particular case if you're approaching the limit from the left or the right per se. So let's just take the limit as h approaches 0, and you get negative 11 over 2 times the square root of 6, which you can approximate with 2.245. If you graph the function as you're approaching 0 here, right, it looks like you get, so sorry, that should be a negative 2.245, right? I mean, it looks like that's what you get. And you'll notice that it looks like you're approaching the same value from the left and the right. But remember, I may not let you use a graphing calculator for these problems, so try to make sure that you know how to do them algebraically. And even if you use a graphing calculator, right, it's really kind of hard to tell exactly what that point is, whereas this gives you the exact answer. Here's the graph of sine of theta over theta. So looks like this. You actually have a hole here at 0, because when theta is 0, this is undefined. But it looks like the limit from the right and left-hand side both approach 1. Right? So that means if you take the ratio of sine of theta divided by the angle, it looks like it's going to be 1. Now the question is, how could we prove that? Well, there's a couple different ways you could do that. We could maybe use a geometric argument or the sandwich theorem. This is just one result you can use from now on if you want, but let's actually prove it. So this is the figure that we're using, and so what I want to do basically is show that this length over this angle, right, is less than 1. So what I'm going to do is I'm going to use a sandwich theorem argument, and so I'm going to sandwich the area area of this sector, right, which is given by this. Remember, the area of a sector is 1/2 the radius times theta squared. So the radius in this case, or the radius in this case is just 1. Or I'm sorry, it's the radius squared times theta, I think. The radius is just 1, so you'll just get 1/2 theta for the area of the sector. If you look at the area of triangle OAP, right, that triangle would be less than the area of the pizza-shaped sector there, right? And the area of that would just be 1/2 times sine of theta, right? Because it's 1/2 the base, which is cosine theta, times the height, or I'm sorry, the base of that is length 1 times the height, which is sine theta. And then you have this larger triangle OAT, which is larger than the area of the wedge-shaped, pizza-shaped sector there. And the area of that would just be 1 times tangent theta, or 1/2 1 times tangent theta. So you can sandwich the area of this wedge in between the area of that triangle and that triangle, and then just take basically take the limit as theta approaches 0, right? Or I guess you could divide everything on both sides by sine theta first if you want to, and then you could flip the direction of the arrow. So if you take the limit as theta approaches 0, that's 1. Well, that's 1, so that forces this thing to be 1 also. So I guess you can do it by just sort of looking at the graph, but it is nice to have sort of an algebraic proof of that as well. So so that might be one result you might want to just kind of put in your toolbox, and I'll kind of just let you use that from now on. You don't necessarily have to prove that every time you use it now, but the proof does depend on the sandwich theorem. So there's one application of the sandwich theorem. So let's look at some example problems. I think these are similar to problems like 21 through 41 in this section of the book. Well, let's say I want you to find this limit here. And you'll notice this is neither right or nor left-hand limit here. What would you want to do? Well, one thing you can do with a fraction like this is you can write each term over the fraction individually. So I can write each numerator over this individually, and then I can reduce, right? So this becomes theta over 2, this becomes negative 1/2, and this becomes 1/2 sine theta over theta if I just move the 2 out in front on the bottom. The limit of this will be 0. The limit of that will be, the limit of a constant is just a constant, so that'll be negative 1/2. There's no theta in here. And if you look at this, right, this will be 1 by the argument we just used. So we'll get negative 1/2 plus 1/2, and that'll be 0. And if you do graph the function, you can see that as theta approaches 0 there, right, you do get height 0. Here's another example. What about sine of 2 theta over theta? You might assume that that would approach height 1 also, but if you were to graph it, it looks like it approaches height 2. So you might wonder what's going on here. I guess one way you can think of it is what this theorem really says is as long as you have the same thing inside the function and the same thing on the bottom and they're both approaching 0, so if you have like sine of some stuff over some stuff and they're both approaching 0, you should get 1. So as long as the thing in here and the thing on the bottom are the same, and you take the limit as theta approaches 0, you should get 1. But in this case, unfortunately, they're not the same. Right here I don't have a 2 on the bottom, but I can sort of change that by multiplying on the top and the bottom of the fraction by 2. And again, that might seem kind of weird, but I can do it. It's as long as I multiply on the top and the bottom by the same thing, it should preserve the value of the fraction. I'm just going to take this 2 and move it out front, and take this 2 and move it down there with a theta. And then if I take the limit as theta approaches 0 of sine of 2 theta over 2 theta, that will be 1 by the previous theorem. So I'll get 2 times 1, or just 2, right? Because that's a constant that can just come out of the limit. So let's say you have something like, say, sine of 3 theta over sine of 2 theta. Well, again, I don't have 3 theta on the bottom here, so what could you do with this? Well, one thing you could do is you could multiply on the top by, say, 3 theta over 3 theta, multiply on the bottom by 2 theta over 2 theta. Since these have the same thing on the top and the bottom here, and they're, if theta is approaching 0, these will both go to 0. That's going to be 1, and that's going to be 1. So you'll just wind up with 3 theta over 2 theta. Those will cancel, and you get 3 halves. And again, that might seem kind of weird, but if you actually graph the function, if you graph sine of 3 theta over sine of 2 theta, you can see that as theta approaches 0, right, it looks like the height of the function is approaching about 1.5. Right, 1.5, which is the same thing as 2/3. So try, you might have to use some tricks like that. Here's another example. So I take sine of, and I guess you could just take the limit of each one of these things separately, provided the limit exists, right? So sine of theta is equal to 0, right? But cotangent of theta, that's undefined. So again, maybe you'll have to use some sort of trig identity substitution or something. You can write cotangent of 2 theta is cosine of 2 theta over sine of 2 theta. And I'm not saying this is the only way to do this. There might be other ways you can do this one. And then there's a trig identity that says that cosine of 2 theta is 2 cosine squared theta minus 1. And remember, sine of 2 theta is 2 sine of theta cosine theta, right? We reviewed those identities in our last chapter. And so what you can do with that then is you can cancel that sine theta with that sine theta. You can also cancel the 2's. And then you can take each term on the top divided by cosine theta. Oh, sorry, I guess I can't cancel the 2's here, can I, right? Because I'd have to have a 2 in this term. So I can cancel the 2's in the first term, but not the second one. So take the limit as theta approaches 0, right? Cosine of 0 is 1. This will be 1 over 2 times 1, so I'll get 1 minus 1/2, or a half. And if you were to actually graph this function, you would see that as theta approaches 0, right, if this is the theta axis, it does look like it's approaching height 1/2. Okay, so hopefully that gives you at least somewhat of an idea of what to do with that section. If you guys have questions or anything, as usual, let me know.